Okay, so we are ready to get started with our final module for the day. Thank you, everybody, for sticking it out with us today. We know these are long days, but we appreciate your time and attention spent with us today and for the rest of this week. So this session will be a little bit different from the other sessions. We're actually going to have three different kind of roughly 30-minute activities for us to work through. One presented by Joel Vanin, one presented by myself, and then one presented by Pedro. So just as a reminder, all of, as with all of the other sessions, this is being recorded and live streamed and will be posted to YouTube for future viewing. And you can find the materials necessary to follow along in the student materials folder. I'll go ahead and turn the screen share over to Joel, and I'll get these links posted in the chat in the meantime. Okay, Joel's already posting his. So I will let Joel go ahead and take over for now.
All right. Yeah, I posted in the chat a link where people can go and grab this simulation that we're going to use here. It has the name of wetting. It's a zip file, so take your time to unzip that because we're going to use it. As Hayden have said, today, this time, we're going to actually play a little bit and do some experiments with these simulations and see what we can gather out of it. Just to remember, we're on the last section, so but there is more for the other days over here. So the learning objectives of this module is to introduce people that don't have a background in physics of what is the problem of wetting, why it's so important to understand that concept in CC3D, and this type of simulations that we do here. Then we're going to actually play with that simulation for a while and try to get some answers or see some results, what changes when we change some parameters. So for those that don't know what the physics of wetting is, it just describes how a liquid spreads or it adheres over a surface, right? So we have here a couple of examples. It's very common nowadays for us to have piece of clothes that are hydrophobic, but other parts, for example, like the windshield of your car, might have some properties to make it a little bit more hydrophilic, so you can actually see properly through a thin sheet of water instead of small droplets of water that would probably scatter the light a little bit different and you would not be able to see very well. We see that effect, for example, when we're in a mist, right? If you shine a bright light on a mist, there's so many small particles that it's difficult for you to see everything. So in some companies in an industrial process, they apply something in those windshields so people can actually see better with a formation of a bigger droplet of water or even a thin layer of water. So the important thing that we're going to see here is how these surface tensions, here is shown, this angle is calculated by the height and the arctangent of this, the contact area versus the height. And we're going to see how that influences the definition of what is wetting or no wetting happening in this the simulation especially. So adding wetting in the context of CompuCell, why is important for us to understand this? It's because that's basically, I don't think I ever seen a simulation that doesn't use the contact plugin at all. If we're doing one single cell, it still has these interfaces with the medium, right? And for morphogenesis and how cells organized, earlier today I presented a little bit about epithelium sheets And there we have very specific cell types in very specific places. So this is how those cell types interact, is mostly by the contact energy. Here, the Young's equation takes in consideration that describe the tension between solid and liquid, liquid and vapor, and solid and vapor. But in CompuCell, we actually have contact energies, right? So the equivalent, I'm even using the same language over here, is cell medium contact energies, plane and medium contact energies, and cell and plane or cell and substrate contact energy. When we learn how these three come together, we can definitely understand a little bit better what we have to do in case we need a cell to crawl on top of the other or to form blobs, beads, and things of that nature. Also, parameter tuning, we're going to see that the more cells you have here, the more cells types, it requires a better understanding how one change in one parameter might affect other parameters, right? So without further ado, let's try to initiate that simulation. If everybody can go to your downloaded copy and unzip it, do the same thing of opening player, and then on player, we're gonna open a simulation file and click on that wetting one. Thank you for initiating the pool. Yeah, let's see if can you see my screen now with or is it still on presentations mode?
You're okay. Your screen's just sharing your desktop.
Oh, okay. So you can see here, right? Yeah, this one over here, I think you can click on these three dots and it has the download over on this side. Yeah. Then you need to unzip this folder before we use it. It'll be on your downloads. Extract
Why don't
all.
you have them unzip it with Twit? Why don't you
Yeah,
show
you
them?
can also.
Why don't you
You can.
launch it and show them how to do that?
I have to open Twitter here. Just give me a second. So, as James suggested, we can open Twedit and unzip it on Twedit. You just go on the project, open project. Mine is on the downloads. Unzip it, and then you select it on the downloads, wetting. And now you go back there, it will open again for you. Just give me a second. And you open project, wetting, it will be there. Oh, my Twedit crashed.
But just open it in Player then.
Right. You might need to adjust these windows.
So why don't instead of trying to open it with Twit, just show them starting from the beginning how to open it in Player.
So the way to open in Player, you go on File, Open Simulation File, your downloads, because it's probably sitting there. Go to the wetting, and the first one, that is the CC3D file.
Go ahead and do it to make sure it works.
Then you might need to adjust these because I use 4K monitor, so sometimes the adjustment is not optimal for other people.
Just use tile.
Right. So is everyone able to see this single cell over here, the steering panel, and the plot? Maybe initiating another poll since 7 people were asking for more time. Anju, if you don't see it, click it over here on window and then tile. That will probably tile everything together and you'll see it. You see better. Okay, so I think I'm gonna move on. Although I think 2 people still that need help.
Joel, can you repeat how to fix everything in one window? I have several windows open now, and I also want to have it in one.
Yeah, yeah. So to put everything in one single space, you just go on window over here. Oh, you're on a MacBook, right? For that, it will be on the very top where the symbol of the apple is. You move over there, you'll find window, and then you click tile. If you don't see this, oh, if you moved these things around and you don't see the cell anymore, yeah, there is a chance of you to kill that cell. It's true. Especially if you put a lot of gravitational force over here and a high or low energy contact, it will squeeze everything until they disappear.
Actually, I don't find it. Sorry.
Mhm.
I am, when I click on the single windows, graphics and contact angle over time, this obviously is opened in Twedit. And the other things,
Right. Oh, so you're looking at the code on Twedit right now.
I just opened it. I don't know. No, I don't look at the code. I still look
Mm.
at the code of my exercise 1.
Okay. Yeah. So did you open it here on file and you find this wetting file? You have to go on the file open.
I opened it in the player and then I said play and 2 separate windows appeared which are freely movable. Let's put it like this.
Yeah. On Apple, it appears as separate windows, right? It doesn't stay in the same
Ach so,
main.
okay.
Yeah.
So this doesn't disturb the code or the program.
Okay. Yeah, it doesn't show the code. Yeah, you will see these
No,
windows
it
are
was a question. Does this disturb the lesson?
if that stops the lesson. Is that what you asked?
Is it a problem that it opens in two
Yeah,
windows?
is it
is
a
what she's
problem
asking?
to
No,
follow
no,
the
it's not a problem. You can just
Ah.
organize them in your field of view. You put them where you want it, like instead
Okay.
of moving, yeah, you can move them where you want it.
And as I said, they are all in tweeted or tweeted.
Is someone able to help her visualizing it in another room or something?
You can do that. Do you think you need to join a breakout room, Catherine?
Yeah, I don't know what we are supposed to do. If everything works fine, I don't need that. But
Yeah.
So
Can you see the three windows clearly?
yes,
Like
yes,
with-
I see
Okay.
everything.
And it's fine.
Okay, so it's fine.
It's just the only thing is if you can't see a window. So some people are saying they're not seeing the windows at all. Liam and Yasmina seem to not be seeing things. So if that's the case, then maybe we need to get you some help. So if you're having trouble getting a screen where you can see all three windows, please put your name in the chat and we will get somebody to help. So who was having trouble? Mohit, Yasmina,
Kimberly.
Kimberly.
So Kimberly, sorry, go ahead, James.
Yasmina says it's working for her. Kimberly, do you want to get some help?
Yeah.
Okay, Pedro, could you take her, Kimberly, to so you say you're having trouble. Somebody says they're having trouble getting a third window, but the windows are not, you don't have to create the window. They create themselves. So why don't you join that breakout room? Sharon, why don't you go try the breakout room too?
I don't need help unless you're asking me to help them.
You might help them since you're a Mac person. So Yasmina, the window was there, but it was hidden. That was the issue. So initially, perhaps the window is behind another window. So when you tile, it forces the windows to be visible. There was
Yeah,
a question in the chat.
yeah, good question, Irene. It's because you will see that it behaves a little bit different, right? There is a lot of fluctuations, and in the calculations that we can get to the Young's module is always the same value all the time, but there is an error. You will see that error. So this will show you what are the errors that we can find when we do one method or the other, and compare them. Yeah. So that's an interesting thing. Maybe I should move on and just say what we're trying to look here is what these angles actually mean, right? So if you have a small angle, it means a good wettability, and a large contact angle means a bad wettability, right? So beating up. So try to play with it a little bit and see if you can have these four formations where the cell spreads moderately with the substrate, showing a little bit of good wettability, right? The other one, it becomes a bead. So this is a high contact energy over here, or contact angle. One other one that it completely detached from the substrate. And the other extreme when we have a full layer or a full wet surface. See if you can play with those parameters and accomplish all of them. Yeah, the thing about the gravity is in the case of this, right? If you raise it too much far away from the surface, the only way for you to getting it back is if you apply a force so it can come down. Very nice, Omar. Yeah, Yasmina is, yeah, in future lectures, we're going to show how you can actually tell the cell to obey a force applied in any direction. In this case, the gravitational force is applying in the downwards force.
So maybe we could ask some basic exercises. Start with the case where it's touching the substrate, and then adjust the cell substrate contact energy. Make it smaller. And ask the question, do you expect the cell to spread on the substrate or to become rounder? And then check whether you get what you expect. And then why don't we people do that as the first exercise? Okay, so someone says if you make the substrate cell contact energy small, the cell spreads on the substrate. So everybody see that? Now you can increase it again and get something like the top right. Try to find a set of simulation conditions that'll give you the top right. And now you can, what happens if you decrease the cell medium contact energy? Does the cell round up or does it spread out?
Yeah, it does do it on the go, Yasmina. It doesn't have, you don't have to stop, but in case something breaks or look weird, you can restart the simulation by pausing or stopping, playing it again. You can also test what is the difference of you initiating with different parameters. What it can do.
Maybe, Joel, it's worth walking through things where you show how to change one energy at a time and ask people to guess what's going to happen before you do it.
Okay.
Avishek, question?
Yeah, so I'm having trouble understand or interpreting the graphs. So for the various configurations that I'm getting.
Mm-hmm. Let's try to understand the graphs over here. Mine is broken. I don't know if it shows. Does it show for you broken, James?
It's because of the zoom.
Oh, okay.
So if you close player and open it again, it should be all right.
A close player and not just a window.
No, well, try close. You better close player.
Yeah. Okay.
Unfortunately, Zoom does something to the scaling of the images.
Yeah. Yeah. Or maybe I should share the other window. So here, I don't remember who asked about the graph. We're just comparing the actual contact angle we are calculating given that height and the contact area between the cell and the substrate versus the expected Young's equation result. So we're trying to see here what is the difference between the two. There's a lot of other things happening here. Whenever you change these values, you'll see that there is a relaxation time until the green actually get to the estimate value of the red. Right? So that is teaching us another thing about how these simulations work, that it takes time for it to go to a certain configuration, right? It's not immediate as the Young's equation. And then after that, we can also see what is the margin of error between what is estimated by the Young's equation and the contact angle that we're actually measuring. Because we have to remember that being on a lattice, things behave a little bit different than what we would expect in a perfect resolution, like a real world resolution.
So is the result kind of like the two things, or the error between the contact angle and the one from the Young's equation, stem from the fact that there are some fluctuations in the boundary of the droplet?
Right. Yeah. That's one, right? Because the fluctuations keep happening, we have a change in the height and the amount of contact that we have between the two, because it fluctuates so much given the temperature that we are, right? If you would see, like we saw that word temperature that James presented, if you lower that temperature, you'll see that there will be less movement. But there are other things that we can do that lowers that temperature too. Not the temperature per se, but lowers a little bit of the relationship between the two.
Yeah.
Right? If you increase the cell medium contact, you start to see that cells don't want to explore as much the medium or the other surface, so they become more squarish, right? Going back to that 90-degree kind of angle.
I see.
So there are some explorations that you can do here. What changes if you make one too big versus the others, right? Does the cell freezes? Because this will happen too. If you increase this too much,
Yeah.
you'll see the cell freezing.
Yes.
Mm-hmm.
Okay.
It might be a little bit counterintuitive because we're increasing, but you have to understand that we're dealing with the minimal energy here. So we're trying to minimize energy. That's why a smaller cell medium contact energy means they're more favorable.
I see. So, okay. Can we just once show the slide that has the Young's equation?
Yes. So let me go back. So this is the angle calculated by the Young's equation, right?
Yeah.
And this one is the one that we are actually using to calculate the contact angle
Oh, I
based
see.
on
Yeah.
based on the height and it's because otherwise we would have to use a spline, and there is the way the edge is detected in CompuCell, it also reports an error, and this way is easier for us to see that angle.
Can you define the terms again on the arc cosine equation? I wasn't just quite clear on how these terms are being. I understood the radius, but I wasn't quite sure plane medium versus cell plane.
Right. So yeah. So right here we have the surface vapor, which in CompuCell is actually plane medium contact energy, right? The solid vapor is the same as plane and medium contact energy minus the solid versus liquid contact energy, or cell plane contact energy here, which is this tension, divided by the liquid and the vapor, which is the cell medium contact energy in this case.
Okay. Okay, I see.
Is there a way to decrease the noise in the boundary of the droplet as it evolves?
Yeah, so there are a couple of ways, right? If you decrease the temperature is one of them that we were saying, and the temperature here is the number of attempts that you're actually trying to make this copy. That diminishes a little bit. But also if you play with these values, you can try to find one that there is not as much noisy. But noise is inherent for this simulation, right? Because it's trying to move and change its shape constantly. And in the code, if you are curious about looking at the code, you can look at it. We are reporting every 10 Monte Carlo steps and not every single Monte Carlo step, because otherwise it would be even more noisy.
Okay.
So that's another way that you can like account for it.
Okay. Thank you.
This is more of a math term, but how are you relating tension and the two equations? Yeah, here it's height and radius, just geometries. But then in the other graph, you're showing tension between two different surfaces.
Right.
Right?
This is actually, this one that you're seeing here is actually what the Young's equation comes from. He actually is looking at the tension, but in CompuCell that is signified by the contact energies, right? In this situation. So this is another way of deriving the same calculation that we saw, but instead of using the Young's equation, I'm using geometry to get to that. That's interesting that you're saying, Sharon. I didn't know. I haven't tested this on a Mac. Good to know that it's not working properly. Yeah. You can modify them in the editor and change them to a Dropbox. Can you change the code on the to edit and see if you can transform them into Dropbox instead of sliders? Sharon?
I have the steering panel and I can change.
Oh, you do?
I can change those sliders, but somebody was saying they don't have the steering panel and trying to figure out how to change them in the model editor.
Oh, I see.
And the model
Yeah.
editor seems messed up to me because there's no numerical values to change.
So if you put something into a slider, then it's not available for steering in the model editor. It's a choice.
Uh-huh.
So you can't do both.
Well, this was true for me in the other simulations as well, so I'm not quite sure where there were no steering panels.
Okay, that I can't tell you, but it won't work. If you've got the sliders active, then you've overwritten the model editor. Okay, there's some technical questions about simulating more elaborate aspects of wetting. I'm not sure this is the best way to do detailed fluid dynamic calculations, but yes, in fact, you could do a lot of these. Joel, why don't you just walk them through very quickly, tell them what the meaning of each line in the slider is, and then show them the one at a time what happens when you increase and decrease the value of that slider. And then we'll go on to the next one. Yes, the temperature you should be able to change, although I'm not sure it'll pick it up. You can try it, but you can pick it up in the model editor. Again, people are asking relatively sophisticated questions, which is great, but these are designed to be fairly simple demos. So some of them you may have to explore on your own after the session.
Right. So when you start the simulation, if you leave it as is, right, every contact energy here is the same. So there is no favorable configuration. We can see it by the expected Young's equation result that it should be a 90-degree angle. On the simulation, we are a little bit above that when we calculate the height versus the number, the contact area underneath on the substrate, right? You find that this angle, again, we're a little bit above it. But when we start moving these sliders, so if I move in this direction where I'm increasing cell plane energy, what should happen? What do you guys think should happen?
The contact angle will be bigger.
Yeah, the angle becomes bigger. Yeah, that's right, right? Because we are making unfavorable for the cell to be in contact with that substrate. And here you will also see a relationship that 20 is the max we can go, right? You can see by the Young's calculation here for the Young's equation that we are on the 180, right? And this angle here can only go up to 180. More than that, we are gonna come out of the substrate. So if we do 21 over here, you will see that will take a while, but this cell will detach from the surface, right? And here you can see that the Young is reporting 181, which is not, because there is no solution, right? I am enforcing 181 here, meaning you're completely detached. You're not attached to the surface anymore. And you will see that slowly but surely, this contact area between the substrate and the cell is becoming smaller and smaller until it hits a point that it will detach. But because it's so small, the energy is so small still, right, for the size of the cell and etc., it'll take a while for that value to reach. So yeah, if you have any question, feel free to ask.
So why don't you go back to the 10, 10, 10, and then change the next, explain what the next line is,
Mm-hmm.
and then
Yeah,
change the cell medium contact energy.
right. I just wanted to show, I don't know if you guys saw, but it detached for a, there you go. Hot second, it detached, and now it detached forever. Right, so we know that the Young's equation is reporting right, and also the simulation is doing what is expected in this case. If we go back to the 1010, now it's favorable. It wants to touch that surface again, and we should go back to the 90-degree angle again. And you see that there is also a phase of relaxation for that simulation for that to be correct, the angle to be correct. Right? There we go. We're very close to getting it the right values again, giving the error. Before I move to the cell medium, so we know that it detaches if I go to this end. If I go to the opposite end, right, the cell should spread its way. But there are two ways of us getting the same result, not only changing, but changing a different energy.
Increasing the cell medium.
Right. If we increase the cell medium, what is going to happen?
The denominator gets really large in the equation. And the theta or whatever it is gets smaller. The angle gets smaller.
Yeah. So let's see, let's go back a little bit, let it relax back to the 90-degree, and then we apply a little bit more contact energy between these two. So when I move in this direction, yeah, you can see if you do more energy, actually the cell will lose a little bit of the noise, right? Because it's now not favorable to explore the medium area. But even to go on top of this surface over here, it needs to go a little bit towards the medium, right? So that's why we don't see this cell changing too much in shape. But if we increase this one, what should happen? The plane medium, the substrate medium.
Our angle gets bigger and
Right.
reduces wettability.
Yeah, right. That solution that you said before, where we have the contact being more wettable over here. Yeah, so
This-
that go ahead.
Sorry, this wooded angle is smaller, right?
Yeah, the contact angle is smaller. Mm-hmm. Yeah, that's basically what I had planned for us to do. Just experiment seeing these results. If you were not able to get any of the solutions, here's a quick answer. And if you want to know more about it, you can ask me later, send an email, and I can guide more about the simulation to you guys. Thank you. Question, Abhishek?
Yeah, I have a question. So in the simulation, you showed how the equation from Young's equation, the angle from the Young's equation and the simulation kind of like disagree, but at what place in the Young's equation or in the numerical equation do you include gravity?
Oh yeah, the gravity, it's not considered on the Young's equation. That's a fair point. Gravity is only there in case you have a detachment of the cell from the substrate that is too big that you cannot make them come back just by controlling the contact energies. So if you increase too much, you can make the cell detach. And even if you change the parameters again back to what you want, you will see that the cell is not able to get back. You have to put a force so it can come back. Or you decrease the medium a lot and then it becomes just dust and eventually it touches and then you can try to change that.
Yeah, I understand. So kind of like the effect of the gravity can be modeled into the numerical calculation of the theta, but I don't see how you can include that in the theoretical calculation of theta from Young's equation.
Right. So there are papers. Yeah, there are papers, and we can discuss this a little bit more in just the two of us. That shows that you have to some measurements for you to validate your model. You actually need to account for it, for the gravity. But if you want to talk more about that, we can set aside a time to talk about it.
So it is kind of like encoded in one of the parameters that you used in order to calculate the theoretical value for theta, right?
Right. Yeah. Sorry, I didn't catch everything you said.
Sorry, we're going to have to move on here because we've got
Sorry.
two more to do. While Pedro is setting up, Abhishek, it's a good question. I don't mean to. But so you can calculate from the force balance equation. You can calculate the angle with gravity included, but it's a little bit more elaborate to do it.
Okay.
There was a question about CompuCell, which is in CompuCell, if you know what the gravitational force is, you can certainly introduce that into the simulation, and we'll show you how to do that. It's in the simulation. We can show you how that works. But the analytic calculation is a bit of a mess when you include gravity, which is why we didn't do it in this case.
Thank you.
But actually, Wikipedia will show you how to do it, I believe, if you look it up. But it's not so pretty.
Should I start?
Go ahead, Pedro.
All right, so please everybody go to the student materials demo folder and download the collective migration zip file, then unzip it, extract the content, and then open the .cc3D file into edit. So while you guys do that, I will quickly provide a biological background and the physical explanation, let's say, of how we implement this specific type of migration in CompuCell and how we achieve collective migration. So the learning objectives are basically getting familiarized with simulations in CompuCell and learn some basic concepts of collective migration. So collective migration is when you have agents and they behave in a correlated manner. So neighboring agents will have correlated behavior. In the case of migration, correlated velocity. Thank you, Hayden, for providing the link. So in this video here, we see a school migrating, and you can see that neighboring fish tend to co-align their velocities. And down here, we see the famous Vichek flocking model, which is used to model, for example, schools and birds too. Collective migration requires active motility and cohesion and communication between agents. You need to transmit information between agents so that speed and velocity, I should say, can correlate between each other. Cohesion can be achieved via adhesion forces, for example, and active motility can be achieved via forces. In the explicit force migration in CompuCell, we define an absolute value for force and a direction for force. The direction varies in time according to a noise. So this would be the equation of how we update the force vector in time. So the next force vector is the previous force vector plus a noise. And it conserves a little bit of the previous force vector, where beta is how much of the noise we are introducing in that previous force. So in CompuCell, this is how it looks like. This is an explicit force model. And the important parameter beta is the noise. If you set to 0, the cell will always migrate in a straight line. If you set beta to 1, the cell will just jiggle and there will be no persistence at all. Then we take that previous force model, let's say, and we update that force based on the displacement of the cell. So if the cell displaced by a delta R, we will sum this delta R. This will be a contribution to our new force vector. And this contribution is multiplied by this 1 minus alpha. Alpha, this parameter, being how much of the force, the previous force, we are conserving. So alpha can also be interpreted as a persistence here. So the more you conserve of the previous force, the more the cell will keep migrating in that direction. But when you consider the cell displacement to calculate the new force, it means that any interaction between the cell and anything happening around it will have a contribution to the force. So whether the cell is in contact with neighbors and whether there are, for example, fluctuations from the Potts algorithm, volume and surface energies, and the explicit force itself acting over the cell, these will all contribute by causing the cell to displace. The important parameter here, alpha, if it's 1, you have no contribution from displacement, so the cell will keep migrating in the same direction all the time, and alpha equals 0, no persistence. By implementing that, we get collectivity. So I will not get into details on how this collectivity thing is measured, but it's basically a combination of rotational velocity of cells and co-alignment of velocity between neighboring cells. And if you sum that to all cells and sum both contributions, you get a general, let's say, collectivity of your system. So these two videos are different cases by changing with different alpha parameter. And you can see clearly that the left one has more collectivity than the right one. And this is just another model. It doesn't use explicit force, and you can achieve migration patterns and collectivity in a different way. So please take your time to load the simulation, and we'll start doing the exercises.
I have a question. On
Go
the
ahead.
force slide that you showed the two force equations update. So just I want to clarify, the first one was with the alpha parameter, it just decides the update of the direction of the force, and the beta parameter decides the magnitude of the force?
No, the beta parameter doesn't decide the magnitude of the force. It decides the magnitude of the noise. The noise is that thing that acts over the direction of the force. So the direction of the force is changing, is fluctuating, and the intensity of this fluctuation is the beta parameter.
Okay, thank you. And can you
Right.
show the alpha equation once more?
Sure. Yes, Avishek?
Yeah, so can you show the slide with the phi and the gamma?
Sure.
Yeah, so I was wondering what are the physical significances of these parameters and what is the physical significance of O square? Like what are the
Sure. So the physical significance of phi is the co-alignment of cells, of the force acting over the cells. So if all cells are migrating in the same direction, phi will be 1.
Okay. Okay.
And the lambda parameter is in respect to the center, how much the cells are rotating to the same direction. If they are rotating in the same direction, all of them rotating the same direction, gamma will be 1.
Okay, so is it kind of like the average translation and average rotation?
Yes.
Okay, got it.
Yes, it is. And then you have to sum the squares because they can be negative.
Yeah. Thank you.
The data figure, there is no data and it's correct. There should not be any information there. You can close that window. So I will load the simulation now. Let me divide my screen. So, for a second, I thought something froze in my computer. Okay, opening player. This is the simulation. I hope you guys can see. Let me click tile.
Maybe change the color so the cell isn't dark gray.
Sure. Are you guys seeing the simulation? Okay, everything? And also, are you guys in the same page here? Is this what you guys see?
Yes.
All right. So first exercise, exploring persistence and noise. So what I want you guys to do is to set a very high persistence, force persistence, and look at what happens. So if you set persistence to 1, what is going on there? Do the cells change the direction of their movement? I see this cell, this alone cell here, for example, it's migrating to the same direction all the time. On the other hand, if you decrease the persistence a lot, it's almost as if the cells have stopped. Right? So there is a certain high persistence where you see the cells changing direction, but migrating quickly. And how about the noise? So by default, the noise is 0. So the only contribution, the only change to the force are the fluctuation, the Potts fluctuation, the interaction between cells, and the volume and surface constraints and contact energies. If we introduce a noise, let's say a very high noise, the cells lose all their persistence. As we reduce the noise, they become more and more persistent. By default, I leave the directional noise at 0 because we already have fluctuations from other sources. Now let me jump to the other exercise. Exploring surface tension. Let me just see something. Exploring force. Okay, that's our next exercise. So we were exploring the persistence in the direction of the force. Let's now explore the intensity by changing this parameter here, force intensity. Now it looks like the cells are faster, right? And of course, if you set the force to 0, the cells barely move. But I want you to do this exercise with a bigger number of cells. I'm suggesting 30 cells. So go ahead and change the number of cells to around 30. And take a moment to appreciate how the cells connect to each other, forming clusters, and then migrating together. If you increase the force persistence to around 0.9, you'll see that these clusters tend to stay together And as they collide, they co-align and then keep migrating together. Once you appreciated that enough, you go ahead and increase the force intensity to as high as you can and see what happens to the cluster. It disintegrates. So why is it? Why does the cluster disintegrate? We didn't change the interactions between cells. We just changed the force intensity acting over the cell center of masses. So why doesn't the cluster keep together when we increase the force? You don't need to answer now, but it's an important interaction in CompuCell. Yes, it overcomes all other forces in the simulation. Exactly. And even having some co-alignment in the simulation, because we have some fluctuations, the fluctuations will eventually change the force direction a little bit. And then eventually the cells will fall apart. The clusters will fall apart. If you decrease the force to 0, the cells are able to form clusters, but they are not so much able to encounter each other. So as you can imagine, there is an optimal force that maximizes both the likelihood of them connecting to each other, colliding to each other, and also the cohesion of the cluster. Were you able to observe that in your simulation? Give me some thumbs up or thumbs down. Or thumbs horizontal. Okay. I will head to the other exercise, to our last exercise. And this is the most interesting one. We were doing all these tests with a negative surface tension, which means the cells want to stay in contact with each other. They don't like medium. They like contact with cells more than they like contact with medium. But so what if we increase the surface tension to positive, which means now they rather stay in contact with medium than in contact with other cells? As you might expect, the cluster disintegrates and we lose the collective motion. Now I see cells migrating to every direction because they are avoiding themselves. Of course, the cell avoidance will produce some velocity correlation if we dig deep into it, but they don't have the same collectivity as before. Now the challenge for you guys is try to get collective migration with surface tension at 10. This is the challenge. You have all the other parameters. Just don't mess with cell volume and lambda volume. Don't mess with those. Change all the other parameters as much as you want and try to achieve collective migration. I will give you 3 to 4 minutes and then I will do it myself and see if you guys could figure out from your understanding of those basic concepts of collective migration, how to achieve collectivity again. if you're able to figure out, please tell us what was your idea? What was the thought process behind it? Avishek, no, this is not the exercise. The exercise is set the surface tension at 10. Don't change the surface tension. Surface tension at 10, and then achieve collective migration. Collectivity. Fixing surface tension at 10. It's not supposed to be an easy exercise. It's our third and final exercise. You have to toast your brain cells. If you have any left. I don't have any brain cells left anymore. I was playing with this yesterday. And I'm also a PhD student. Of course you can. Increase the number of cells, decrease the number of cells, close the simulation. You can do whatever you want. Just surface tension at 10. And I do not recommend changing cell volume and lambda volume because they don't do anything. It's not that they don't do anything. They don't contribute into achieving the objective. So keep surface tension at 10. And I would not mess with cell volume and lambda volume. Change number of cells, noise, persistence, and force intensity. Yeah. So if you set your force persistence to 1, it means that they will never change the direction. They will always preserve 100% of the previous force direction they had. So by never changing the direction, they will never clump together. Does that make sense? They rather follow their path. Okay, I gave you guys enough time. I will go right to the answer. Otherwise, we will stay here for dinner in the workshop. How wonderful is that? So what I'm going to do here is, so let me think. I need some kind of cohesion to achieve collective migration, something that approximates the cells. But I have to keep the high surface tension. So how can I make the cells closer together without decreasing the surface tension? And the answer is increase the number of cells as much as I can. So I will set a very high number of cells. So now I have a very high density, and now the cells don't have other option other than interacting closely to each other. And now I will do some fine adjustments, for example, increasing the force persistence a bit. Directional noise is 0, and now I wait. I think that's enough. Let's hope. So far, I don't see anything. They are just disorganized. But given enough time, they should migrate collectively. Yes, it does include the alpha effect, the interaction between cells. Yes. And now I think I already see collective movement. It seems to me that all the cells are migrating to the same direction, more or less, which is they are migrating upwards a little bit to the diagonal, to the left diagonal. Do you all see it? So I think I achieved collective migration with high surface tension. I will leave you guys to play with the simulation. It's a very cool simulation. I love this. And I could extract some phase transitions out of this. But unfortunately, ideally, I would do that with millions and millions of cells. But it was getting too slow to run in my computer. In this case, we would need clusters and but this is already a lot and decent material to extract data and do data analysis on collective migration already. So I hope you guys enjoyed. Now we'll launch the questionnaire for you guys to respond. Please answer the questionnaire as it's important for us to calibrate our lectures and make the next lectures better, as well as the next workshop better. Abhishek, please go ahead.
So,
Yeah, I was wondering what is that theta panel for?
So the panel theta is the direction of the force originally. And then I deactivated it for the purpose of this demonstration because since I am working here with 500 cells, it would be 500 points in this graph. Every Monte Carlo step, and this makes the simulation run slower.
I see. Thank you.
Thank you. Anyone else?
Just as a quick note, please do fill out the questionnaire. And we'll still have time for questions for Pedro in a minute, but we'll do a shortened version of our last activity just kind of to get people started. And then if you want to look at it as not homework, but if you want to look at it on your own later, you can do that. So obviously if you need to go exactly at 6, once you fill out the questionnaire, you're welcome to go and we'll make sure you have access to this activity. But if you'd like to stick around for a little bit longer, we'll have another 10 to 15 minute demonstration to get you started on. So I think Miguel has a question for Pedro.
Yes, I have a question. I don't know if you have already answered this question, but is there a way to make the simulation go faster or not?
Yes, there is a way, and you can increase the number of processors, and you speed up the simulation considerably. I would say 2 times from my personal experience. It will make your simulation 2 times faster. But if you don't change your number of processors, no, there's no way. I mean, you can get a better processor, but there's no reliable way to do it.
I have one question. We are trying to recreate the connectivity between the cells, but as I can see from your screen, that they are just moving. All these cells are just moving towards the same direction. And how can we consider that they create some kind of connectivity?
Collectivity. Yeah, so even though they are not in contact with each other, they are interacting via repulsion. They are repelling each other because we set a high surface tension, which means a high contact energy between cells. So they are repelling each other.
Yeah.
And then this interaction will lead to an update to the force because this repulsion make the cells displace. And the displacement is then an input to the new force. So all these interactions between cells result in a correlation between their forces. And over time, unexpectedly, this is not trivial. This is not trivial. You don't conclude from what I said that, oh, of course, it's going to be collective motion. This is an amazing result, an unexpected result.
Yeah, sure. Yeah. Because the surface tension is super high, so they cannot actually interact with each other. It makes sense. Thank you.
I'll
I
stay
stepped
here
away for a moment.
extra.
Are we in Q&A?
Yes, we are in Q&A.
I'm really behind in math. I realize, or haven't been doing much math lately. I'm curious what the importance is for the Greek symbols, if they were used arbitrarily in your equations, Pedro, or if they are important, if it's important to have important to have those specific symbols within your equations, why those symbols were chosen, if they're arbitrary, if they're important.
Sure. So, of course, they are arbitrary. I mean, some of the symbols are not. For example, delta is not arbitrary. It's a variation.
Right.
This bar is not arbitrary. This is an absolute value.
Right.
But if you mean, for example, R is arbitrary. But this is universally how you refer to a position in space by using R.
Okay.
And so if you open, so this is the idea here is to be consistent with what modelers and physicists are using, and specifically those that work with collective migration. So for example, they use this psi, no, sorry, I don't know the name of this letter in English, okay? In Portuguese, we say xi, which is this one right here that represents the noise. Yeah,
it represents
this
noise.
one,
okay.
Yeah, the noise one is universal. Like almost everybody uses this Greek letter to represent noise, and alpha is a common one for persistence, and then beta because we are using alpha and then beta. F for force, T for time. So people that work with this would immediately understand what the equation means, but the focus of this presentation is not so much on the mathematics. However, it is important to have some idea of how the mechanism plays out.
I'm sorry, the Fn minus 1 and Fn, what does this mean? It means that the blue, for example, the Fn means the force between these two blue cells?
No, good question. And I now recognizes that maybe this figure is misleading. Everything in this image relates to this green cell here on the right. Right? So delta R is the displacement of this particular cell.
Yes.
Fn minus 1 is the past force applied over this cell, and Fn is the current force applied over this cell. And Fn, as the equation says, is the previous force, the Fn minus 1, the previous force, plus the contribution of the displacement.
You mean the Fn minus 1 is the previous force that towards that direction. And because the cell, a green cell wants to change its direction, and the current force is Fn.
Yes.
And okay.
The force updates. It's not like the cell wants to move in a particular direction. It is more like the cell happened to have moved to a particular direction. Now, this fact that it moved to a particular direction feeds into the next force vector.
And why this cell happened to move to next direction? Because of the different force like has been applied on the cell, like the difference between Fn minus 1 and Fn?
It moved to a particular direction because it is in contact with other cells, because it is fluctuating because of the cellular POTS algorithm. So all these interactions, volume, surface, and collision with other cells will make the cell displace to a certain direction.
Okay, influenced by the environment.
Yes.
Great, thank you.
Also,
No
theta is not included on this page. Why?
Sorry?
Theta is not included on this page, other than calling it direction, but it's not included in the equation or the diagram.
Sure. So force being a vector, it carries both the intensity and the direction. You don't see the intensity and the direction because they are inside this F with a vector above it. But F with a vector above it is carrying the direction and the intensity altogether.
Symbolically, having an arrow above a symbol symbolizes that it's some type of vector.
Yes, which carries direction and intensity. Exactly.
Okay, thanks.
Yeah. I mean, if some of you want to get more in depth in the mathematics, I'm absolutely happy to go.
I did get the recommended mathematical biology textbook that Hayden put in his email.
Okay.
I can take a look, but it'd kind of be nice to have if there is a cheat sheet on mathematical symbols.
Mm-hmm.
You can look for that.
Yeah, it should be enough, and it should use the same notation as the notations I'm using here. Omar, please.
Yes, hello. I don't know if the simulation takes into account the momentum transfer, or is it more like because there are no elastic or inelastic collisions between cells, no? It's just the applied force and the for example, when there is low or negative surface tension, they stick. But the total momentum is not conserved to, or does not reflect the change in mass of the total cluster, right?
This is a very important question. So the non-conservation of momentum and non-conservation of energy is one of the core concepts here. So the cells, when real cells collide, they do not transfer momentum and conserve energy because they are always adhering to something, and then they adhere to each other. So conservation of momentum and energy is not realistic in the scale, in the biological scale that we are considering when cells migrate collectively. So here the way that we solve the cell collision problem in CompuCell is by first, there is a contact energy, there is an adherence, and the communication via the cell displacement feeding into the force is what make them decide, oh, I want to co-align with the cell or not.
So it means that the momentum transfer is like too low that you don't take into account, or is not that important?
We are not taking into account. That's the
Okay.
correct answer. Yes.
Yeah.
There is no conservation of momentum and there is no conservation of energy.
Okay, thank you.
No problem. Good question. So when, for example, this is very interesting because like cells don't collide like billiard balls. Like they collide and then they do this. They don't. They always like do something weird and then do something weird again. So they are not like billiard balls. And in molecular dynamics simulations where cells are billiard balls, they have to do a lot of other stuff in their code to make them not conserve momentum and to make them not conserve energy. So for example, they apply drag forces, or they model adhesion forces, attraction forces to make the cells stick to each other. And or for example, yeah, a thermal bath, that's how they do it, to really take energy out of the system as much as you can when they collide. Go ahead, Vishak.
Yeah, so I was wondering if we can do this kind of like similar mathematics and similar simulations with like chains of cells, right? Well, when for example, if I have a chain of several cells connected together and I two such chains, and if they're colliding, what kind of mechanics will it produce? Like, can that be modeled through this kind of like mathematical setup?
Sure, you can. You absolutely can. And I used compartmental cells to do this. So cells in a chain, I try to come up with this cells in a chain idea, which is observed experimentally. And
Yes.
and I realized I could also achieve other kinds of morphologies. For example, cells migrating side by side, like this one in the middle, and cells migrating in circles, like this one in the bottom, which is pretty cool. Eventually they will, yeah, right in the beginning here, you can see that they start to migrate in circles, which is fascinating. So you can use not only this one, but other sorts of cell interactions to achieve collective migration in different kinds of morphologies.
Thank you.
In this simulation, even we see some filaments forming. They are unstable, but you can see some filaments forming. So yes, even this simulation, which is very, very simple, the one we explore today, you can use to model, to apply to line of cells.
I see.
What is the another model called? I didn't give it a name yet. I was calling it actomyosin migration because I interpret this blue compartment, this blue cell compartment, as a actin network. Which process specifically? What is the process?
Are there any published paper with the mathematical model for the another model put on?
For which one?
For the last one, the another model where the chains kind of like interact and there are some interesting dynamics.
You mean this one?
Yeah. So are there any published mathematical modeling paper on that one?
No. I developed this simulation for the purpose of showing to people the capability of CompuCell in building collective migration simulations. I think it's one of the most useful platforms to do that, one of the most promising platforms, but we never got like interested enough to publish it, unfortunately. Yeah.
That could be a
And-
great hackathon project.
Yes.
Yeah, I'm inclined to do it. Because I'm also kind of like interested since I'm dealing with similar kind of like features. Yeah.
Mhm. So answering Susan, James, do you know if there is a formal name for this process where we update the force based on the displacement? I'm just calling it displacement-based force update.
Well, it's a classic kind of persistent motion. So basically, it's a Langevin process.
Okay, Langevin process. Yes.
But it's also known as a co-alignment process. But I think what you have there is I'm not sure that it has an agreed upon name.
Mhm. Interesting question from Kimberly James. I would love to do one of those, to teach 1 or 2 sessions in a mathematical crash course.
Do you have the link to the textbook that Connor likes so much that teaches all of the math in the context of dynamical systems? That's so good.
I have
Yep.
the one that was recommended, the Essentials of Mathematical Biology. And I was just looking into the section on biological motion, thinking that that might be similar to what the simulation just covered, but I could be wrong because
That won't cover it.
yeah, I'm not seeing it there.
The
This
name
is a fairly specific.
Modeling Life by Alan Garfinkel.
Can you put that in the chat, the link to that? That's actually, isn't there a free copy? Isn't that freely available, that book? I think the PDF is a free download.
Oh,
Give me a
okay.
second.
It starts, it's a nice textbook because it really assumes almost no mathematical background.
Really? Okay. Yeah, I'd
The,
like to get more comfortable.
There-
that one.
Yeah, the real challenge with a crash course on biological mathematics, well, mathematical biology, is how do we get to, for example, the outcomes of a tumor growth without calculus, you know? Because people without calculus background will attend to the course, and I don't have an answer to that.
You can get pretty far without too much math, but there are certainly parts of this that are mathematical, and I think, and again, if you did something like a hackathon, what we do is we try to pair people up. So people who have stronger math backgrounds might work with somebody who's more computing. Somebody who's more computing might work with somebody who's more biological. But But yes, this book that Joel shared is an excellent one for getting up to speed on this. But it takes a while. I don't know. With Python, in a day, you can really teach a lot that you need. To get up to the speed on the mathematics, it depends a little bit where you're starting, but some of the things are fairly simple. Some of them are more complex. Intuitively, maybe what we need here is something that's more intuitive. That suppose that you were walking forward and somebody were nudging you and gently turning the direction in which you moved. You'd keep going forward, but the direction you moved would change a little bit depending on how you were nudged. This is basically a mathematical description of that.
I can see how Pedro would be sad because the math is here is probably so elegant. And yet I also see how having an intuitive situation would be a little easier to follow.
Right. So those are good things to point out. In other words, where we're aware of it, we will try to update the slides to make those things more intuitive for people. The other thing you can do, of course, is one of the reasons you build the simulations is because sometimes working with the simulation, you can see how the mathematics plays out.
Yeah.
So if you don't have the intuition to begin with, you can play with what happens. What happens if I make alpha bigger? What happens if I make beta bigger or smaller?
Yeah, yeah. It just like yesterday when we were talking about creating classes and objects and all of that, I was lost until we had an example. So maybe I was lost in just the symbols here, but trying to explain the math at a higher intuitive level potentially could be helpful.
Basically here, the persistence time is essentially the alpha. If alpha is 1, then the system is essentially, it's like an oil tanker. Suppose you're throwing ping pong balls at an oil tanker. You're not going to change the direction it moves very much. But
yeah, well, actually, Pedro's example of persistence versus randomness seemed to make sense, right? Either going to be strongly on a course if it's 1 or not persistent at all if that value is 0. That made sense.
But it's essentially that you could, if it's not, these are overdamped motions, it's a little bit different. But if you think about inertia, a system with very high inertia has got a lot of persistence. A system with very low inertia doesn't. An oil tanker versus a mosquito or a gnat.
Yeah. Okay.
Are there other?
Yeah. So
there was Jesse. Are there any other questions? Because I just want to make sure everybody has a chance to ask, and then we can come back to this. Oh, go ahead then, Pedro. I just want to make sure that people had a chance to ask the questions if they had.
So this is a very I struggle to find an example to this. Maybe I have one. Maybe I have an example to this mechanism. Very funny one. So the cell is walking to a direction with a force vector Fn, and then in the next step, like in the future, the force vector will be n plus 1. So this is the next one. You have the force 1, the force 2, the force 3, because you have time 1, time 2, time 3. So in the time n, you have a certain force. And then in the time n plus 1, you have another force. That's basically what the notation is saying. And then because in the middle of this, the cell also displaced a little bit. So let's say it was a little bit down here and it got displaced like this. Then I take this contribution and I update that into the force. So now the force should be actually tilted a little bit to this direction. So this is more more like what James was exemplifying with, like someone is pushing you and then you change your direction. But maybe I have a more an example that is more true to this mechanism. Imagine you have a cat and your cat is walking north. And then you grab your cat and you change the location of your cat. And the cat instantly starts walking to the direction that you pointed it to. As if it didn't have any memory of the previous direction it was walking before. And you can actually do that to cats. It's hilarious. They are walking to some direction and then you change them and they walk to the new direction. Like a robot.
Oh, do they change their force over time?
The cats, no. They always walk like
this is a really
that
nice
same
pictorial
speed.
example. I think it's a little more clear than the original image that you had.
But it's super hard because the actual interaction between cells is the best example. And it's based on that. When two cells come in contact with each other, the lamellipodia changes its shape and reorients the polarization of the cell. So it's very hard to find an analogous example in real life that actually implements this mathematical abstraction.
Well, what you just said made sense. That's real.
So the current force is kind of like a weighted average between the previous force and the kind of like a slight perturbation.
Exactly, Avishai.
With a certain probability. So if I am in the current state and a force Fn+1 is applied, and there is also a small perturbation with a probability of beta, then the total force will be 1 minus beta of the previous one, plus the probability of that notch. Of the kind of like, what should I say? Perturbation.
Exactly. Yes. That's it. It's a perturbation, and in this case, the perturbation comes from the displacement. Yeah.
Yes.
Okay, any other questions for today? People have had, I really appreciate how much people have engaged today. The questions have been really wide-ranging, and people have not been shy about asking, which is really important. I hope everybody has CompuCell running and that we can, I know people are probably tired, but if you can play with Player and twit it a little bit tonight and familiarize yourself with how to lay things out, how to recover if it crashes, these kinds of things, then things may go a little more smoothly for you tomorrow.